Okay, kids. So, this is the third time I have tried to do this. I actually got through my video last time, and then the program crashed while um, uploading it. So, now I get to redo the whole video again. So, I am prioritizing the video. I want to make sure you guys have ample time to study prior to the um, final. So what that means is I probably won't get the test finished today. So that'll be a tomorrow problem. Okay. So this video is going to look a little bit different. I'm not actually going to be doing the problems in real time. Rather, I'm going to be looking back over what I already wrote down and um, kind of explaining it. Let's save it though before anything happens. Um, okay, let's go call this final review 24 December. Okay, so this video is focusing on these four problems. The final is going to be 16 problems. 12 of them are going to fall into the category of um, definitions, stuff like that. And therefore, it is, but just because there are 12 of them, only four of these, it's important to understand that point wise, these four questions are going to be worth over half of the test points. So the two horizontal projectile ones will probably be worth about 8 points each. The kinematic equation one will probably be worth about 10 points each, and the non-right vector addition one will be probably 14 points. So that's 16, 30, 38 points. And then you've got the 12 other ones will probably be worth about 24 points ish total. So you're looking at probably 60, 70 points total on the test. And over half of that is going to be these four problems. Why? Because I really want to know that you know how to do the work. It's not just about being able to repeat keywords and stuff like that. It's about actually knowing what you're doing. Sorry about the voice. It's a little scratchy. Two horizontal projectiles, one kinematic equation, one non-right vector addition. That's how this is going to break down. So we're going to start with the horizontal projectiles. So horizontal projectiles, basically, this is your basic setup. We have an object, a ball, whatever, a rock falling off of something, a desk, a bridge, a cliff. And as it falls, it continues in its original path of motion. So if I roll, so you can think about this like a baseball, right? I can drop a baseball, it'll fall directly down. I can throw a baseball, and that baseball will eventually hit the ground because gravity takes over. And so you end up with this kind of parabolic shape. Remember, all objects falling follow a parabolic path. Yeah, so that's good to know. And that's because as they continue moving left to right, this way, gravity takes over. Now, keep in mind, gravity it compounds. So the longer it falls, the faster it's going. So that's why as the ball goes further down this curve, it's dropping at a faster and faster rate. So when we look at horizontal projectile ones, so we have five basic variables that we want to look at. Now notice that we have x's and y's as the subscripts. Time doesn't have it because time doesn't care. And those x's and y's relate to our standard axis, that you first learned way back when. X is the horizontal, it goes left to right. Y is the vertical, it goes up and down. So it is when we're looking at these variables and you have v sub x, that means it is the velocity on the horizontal. How fast are we going from left to right? Delta x is the horizontal displacement. That is how far we moved on the x-axis. Delta y, that is the change in your y position. Remember that triangle is the Greek letter delta. It means change. I'm not sure where that comes from, but here we are. And so delta y is that change in y, your change in vertical displacement. A sub y is your vertical acceleration. I'm pretty sure I spelled acceleration wrong. And that is, for all intents and purposes, always going to be 9.81 meters per second squared. That is acceleration due to gravity. Now, that number can change, especially if you get far away from the Earth or, anything like that. But for our purposes, acceleration due to gravity is 9.81 meters per second squared. And then you have time. So the standard problem goes something like this. An object rolls off of something, or is thrown off of something. And it falls a certain distance, and then we're either given how far away it fell or how fast it was moving when it fell, and asked to find the other one. Okay, so that really gives us two equations. The first of which is this. So this is delta y equals 1/2 at squared. Now this is a kinematic equation that we've adjusted to only deal with the change in our vertical position. So you have the change in y equals 1/2 the acceleration. So what this equation does is it relates three things, and those are the underlines. It relates how far something fell, the acceleration of the fall, and how long it took to fall. So for us, For us, the first step is almost always going to be finding out how long it took something to fall. So we know that when... Hey, sweetie pie. We know that when something falls from rest, meaning that it wasn't being thrown up in the air or hurled down, that the only thing causing it to fall is gravity. So if we know how far something has to fall, we can figure out how long it takes to fall that way. And this is the equation it gives us. we put, and these are arrows right here. Shh, come here. 2 times the distance divided by the acceleration down there. Okay. And then once we have that, we can plug that into a variation of this. So if we're looking for how far away something fell, we take the horizontal velocity and multiply it by time. If we know how far away something fell and we want to know how fast it was going, we can take the distance and divide that by the time, and that's going to give us our velocity. So let's look at, let me find out where I put the problem. Okay. So here's the problem. Here's a little sample problem we're going to do. We have a rock ball, it doesn't really matter, being kicked off of a bridge at a rate of 12 meters per second. The bridge is 20 meters high, and we want to figure out that what the problem is asking is how far away from the bridge does it land, delta x. How far did it move horizontally as it was falling? So as I just said, what we want to do, the first thing is we want to find time. The time. Okay, so the first thing we want to do is take time. Now, if I were you, I would write down these steps on my cheat sheet. Step 1, find out how long it took to fall. How are we going to do that? We're going to use this equation right here. Delta t equals 2 delta y over a sub y. Time equals the square root of 2 times the distance it fell, divided by acceleration due to gravity. And notice what happens here. I plug it in, and I get negative 20 meters and negative 9.81. And the reason for that is when things fall, as you can see the little arrow right there, they're moving downward on the y-axis. So when you move downward on the y-axis, that is negative, right? Up is positive, down is negative. So that gives us 40 divided by 9.81 meters per second squared. The meters cancel out. The second squared flips up. 40 divided by 9.81 is 4.08 seconds squared. Take the square root of that and we get 2.01927. Now we only have 2 significant figures here from the 20 meters. And I think I put a decimal point there to make sure that it was 2 sig figs. I think on the test, you're going to have 3 sig figs. So we count 1, 2. That's where we end. And we look at that 1. The 1 does not round up, so we just leave it alone. So 2 seconds. So we know it took 2 seconds to fall 20 meters. Okay, that's about 60 feet. So if you were to jump off a 6-story building, you'd have 2 seconds to regret that decision. And 1 Mississippi, 2 Mississippi, splash. Okay. So then what we're going to do is we need to find out how far it went horizontally. And that's where we go back to that other equation that we had, which is that v sub x equals, let me try and find it. This one right here, delta x equals v sub x times delta t. Excuse me, sorry about that. We know how fast the rock was going horizontally when it left the bridge, 12 meters per second, right? Now, as it continued to go left to right at 12 meters per second, it was falling. After 2 seconds of falling, it hit the water and stopped moving left to right. So it hit the water. How far did it move left to right? Well, we take our v sub x, we multiply it by our delta t, and we get our delta x. Okay, so 12 times 2 is 24. It moved 24 meters during that time. Okay, so that's the process you want to go through on these problems. You want to, 1, find out how long it took to fall. 2, take that time, plug it back into the other equation based on what you're looking for. If you're looking for how far away it fell, it's really simple. Velocity times time, that'll give you distance. If you're looking for how fast it was going, if you already know how far away it fell, then you just do displacement divided by time. Okay, super simple. Okay, and so I'm only going to do one example for that. So that leads us now to our, actually no it doesn't. In the final, you'll be asked to convert kilometers per hour to meters per second, okay? So the speed you're going to get is going to be in kilometers per hour, but in order to work with acceleration due to gravity, you need to change that to meters per second. The way that you do that is generically you multiply by 1,000 and then divide by 3,600. Or if you're good at your maths, you can just divide by 3.6. Same thing. This is how you do it, though. So let's say I'm going 10 kilometers per hour, and I want to know how many meters per second that is. Because I've already done this, I have 2.8 meters per second here. That's my answer, but let's still walk through it. So the first thing I want to do is I want to multiply it each by 1,000. Okay. The reason is there are 1,000 meters in a kilometer. So if I'm going 10 kilometers an hour, that means I'm going 10,000. I missed a 0 there. Meters per hour, right? If I was going 1 foot per hour, that'd be the same thing as going 12 inches per hour. They're equivalent measurements. 1,000 meters in 1 kilometer, same thing. So that means I'm going 10,000 meters in 1 hour. Okay. Oh, no, I was right. It was actually, I put the 0 in the wrong place. We go take it back. Go away. There we go. Okay. So 10,000 meters per hour. But I don't want to know meters per hour. I want to know meters per second. So I divide that by 3,600. Okay. There are 3,600 seconds in an hour. There's 60 minutes in an hour. There's 60 seconds in a minute. So we go 60 times 60, we get 3,600. So whenever we're going from kilometers per hour to meters per second, we multiply by 1,000 and then divide by 3,600. Okay. Definitely write that down. You will need that on the final. So now we're moving on to kinematic equations. So I feel the shush. My Papa's not happy that I'm still awake. I'm not in bed cuddling with her and my wife. Anyway, so this is basically what the kinematic equation is going to look like. The problem. So same setup. I want you to be prepared for the skill set you're going to have to use. Okay. So in the problem, go outside. In the problem, Andy has souped up a truck, and he decides to take it drag racing. Now, the person he drag races, I think go outside, feet. Hold on, I'll be right back. So the numbers are a little bit different. The acceleration numbers are different, but the process is the same. So here we have car number 1 accelerates at 10 meters per second squared. Car number 2 accelerates at 7 meters per second squared. So what's going to happen is car number 2 is going to get a 2-second head start. And then what we want to know is how fast each car is going when car number 1 passes car number 2. So when car number 1 passes car number 2, they have both traveled the same distance from the start line, right? So here, we're going to know that the distance traveled by car number 1 is equal to the distance traveled or displacement of car number 2. Okay, so those two things are equal. We'll know how fast they're going. So what we're going to do is we're going to look at this equation. So this should be fairly familiar to you. This is an equation that we're actually using to figure out how far something went, but now we're using it for linear acceleration, so for cars. So what we have here is the distance that car number 1 goes is equal to 1/2 its acceleration times the time it drives squared. The distance that car number 2 goes is equal to 1/2 its acceleration times its time squared. And when you look at this, because remember up here, remember that when they pass each other, they're going the same distance. This right here. Displacement of car 1 equals the displacement of car 2. They have traveled the same distance in the same direction, which means their displacement is the same. So what we're going to do is we're going to set these two equations equal to each other. So we have 1/2 acceleration of car 1 times the time that car 1 is driving equals 1/2 acceleration of car 2 times the time that car 2 was driving. Now, here's the thing. We already given their accelerations. Now, because car number 2 got a head start, we don't know how long car 1's been driving, right? But we do know that car 2 is equal to car 1 plus 2 seconds, right? So when we start plugging things in, this is what our equation is going to look like. 1/2 the acceleration of car 1, 10 meters per second squared, times time squared equals 1/2 7 meters per second squared. That's the second car's acceleration. Now check this out, t plus 2 squared. Now if you don't know how to do t plus 2 squared, it's basic distribution. Sound effects help. Come see me either, in class, at lunch, after school, whatever. But what we get when we do t plus 2 squared is t squared plus 4t plus 4. 1/2 of 7 is 3.5, and 1/2 of 10 is 5. So when we look at and we see 5t squared equals 3.5 times t squared plus 4t plus 4, we're going to go ahead and distribute that 3.5. So now we have 5t squared equals 3.5t squared plus 14t plus 14. Now, you've already seen that I'm subtracting everything. Now, if you're one of those people who just naturally gets math, you know where this is heading. If not, let me break the bad news to you. This is a quadratic equation, so we're going to have to run this through the quadratic formula, okay? So we need to get everything together, and we get this equation. 1.5t squared, because we subtracted 3.5t squared from 5t squared, minus 14t minus 14 equals 0. So that gives us a equals 1.5, b equals negative 14, c equals negative 14. And from there, we just drop it into the quadratic formula. Remember the quadratic formula? Negative b plus or minus the square root of b squared minus 4ac over 2a. And that's this right here. Okay? Go away. We have negative b right here. B squared right here. 4 times a times c over 2 times a. Okay, so that's the quadratic formula right now. We just plugged everything in. If you don't know how to do this, feel free to talk to your math teacher, feel free to talk to me, but this is what you're going to have to do on the test. On the test, I think it's only a second early that the other car leaves, so the math's a little bit simpler, but you need to be able to do t plus 1 squared, okay? 14 squared minus 4 times 1.5 times negative 14 gives me 280. Now notice what I do here. It's the original equation is 14 plus or minus the square root of 280 divided by 3. Here I have 14 plus 16.7 over 3, 16.7 being the square root of 280. And the reason is I don't need to do the negative, right? Because I'm looking for time here. My answer is going to be the time that car number 1 has been driving. And if I put negative 16.7, that would mean car number 1 was driving negative 2.7 seconds, right? Can't do that. So we don't need to worry about negative time. It's not a thing. At least not in our reality. And 14 plus 16.7 is 30.7. 30.7 divided by 3, gives us 10.2 seconds, okay? So car number 2 gets a 2-second head lead, and then it takes, because car number 1 is a faster accelerator, it has better acceleration, but it still takes them 10.2 seconds to catch up. But that's not the problem. The problem wasn't how long did it take him to catch up. The problem was how fast are they each going. So that is simply final velocity. So the original equation, now keep in mind that we are looking at work that I already did the first time I made this video. Actually, the second time I made this video. And we get this equation, v sub f equals v sub I t plus at. Because both cars started from a stop, we can just cross out that v sub it, that's the initial velocity times time. The initial velocity in both cases was 0. 0 times time is 0. It doesn't matter how long it's been going. So the first thing we want to do is figure out how fast car number 1 is going. We're going to take its acceleration, 10 meters per second squared. We're going to multiply that by the time it was driving, 10.25 seconds. And that is going to give us, 102.5 meters per second. Very, very fast indeed. Okay. Now, it gets a little tricky with the second car because look how much time. When you're doing this on the final, don't forget that the other car that Andy is drag racing has a 1 second head start. So however long Andy's been driving, 5, 6, 7, 8, 9, 10 seconds. In order to figure out how fast the other car is going, we need to add a second to that time. Here, car number 2 had a 2 second head start. So where car number 1 caught up to car number 2 after 10.25 seconds, that means that car number 2 had been driving for 12.25 seconds, right? the 10.25 seconds that car number 1 had been driving plus its 2-second head start. We multiply that by its acceleration, 7 meters per second, and we get that it was going 85.8 meters per second. Okay, so this problem, wording and everything, is almost identical to the problem you're going to face on the final. So you can literally copy this down as a guide. In the other video, I even gave you the numbers. I believe it was something like 7.9 meters per second, or 5.9 meters per second squared is one acceleration. The other one's like 3 something. And it was only a second difference. So I think it was 3. I think the 2 accelerations were 5.9 meters per second and 3.7 meters per second. Sounds right. Something like that. Anyway. And the time difference was only a second. So you could even write down the sample problem and then write down those numbers. You could practice this problem with those numbers. And probably get pretty close to what the answers on the final are. Again, I want you guys to be prepared. I care more about you guys being able to do these skills. This shouldn't be a gotcha thing, right? So I'm giving you guys as much information as I can. Okay. So here's where things get a little tricky. Where did everything go? I'm going to go down here. Okay. So you guys, as a general rule, kind of struggled on the vector problems on the last test, which, given that it was a vector test, isn't the best news, but it's fine. So what we're actually going to do is we're going to actually walk through the problem on the test, okay? So the problem on the test says that Emerald's gone out looking for coffee, and she travels 480 meters, about a third of a mile, at 16 degrees west of south to her favorite coffee shop. It's closed. She travels 1.2 kilometers at, I think it's 28 degrees east of south, and to a second coffee shop, also closed. So your job was to find this vector right there. Now, this drawing confuses a lot of people, so I'm going to do 2 things here. One, I'm going to kind of show you on one drawing what we're doing, and then show you a simplified version. Okay, so really what we want to do here is we want to solve for this triangle, figure out how far south we went, how far west we went. We then want to solve for this triangle, figure out how far south we went, how far east we went. And then when we add all those up together, that's going to give us this triangle right here, which is going to tell us the total amount south we went and how far east we went. How do I know we went further east? Because I've done this problem several times. Anyway, so that's a hot mess. I'm assuming most of the people looking at that are going, yeah, this is why I quit, and just guess at the answer. Okay? So let me show you kind of an easier way to do this. And this I'm going to kind of walk through separately so you guys can actually see it come together. So what I recommend is, we know that step 1 to we know that step 1 to solving this is to break apart the vectors into its component parts. Okay, so we're going to do that piece by piece. We know this is 480. We know this is 16. And so we're going to solve this triangle right here. We're not even going to think about the other triangles right here, right? So we know This is the adjacent side. This is the opposite side. Do not have the time nor the want to go through and do an entire another lesson on trigonometry. So this is but if you do need one, like please understand, like I'm not saying that I won't help you. If you don't understand sine, cosine, tangent, that stuff, and you need help with that, please come in, like just ask, say, hey, Mr. Renard, I don't understand trigonometry. And we'll work on it together, okay? I'm just not going to spend the time right now in this video to rehash the whole thing. So this is going to be 480 cosine 16. And this right here is going to be 480. Sorry about that. Sine of 16. Okay. Make sure you know how to do this on your calculator. So we're going to run that through our calculator. And we get that this is 132 meters. This is 461 meters. Okay. So this is how far south they went on she went on that first trip. This is how far west she went on the first trip. Okay. So now we've got that done. What we're going to do is we are going to now do the second triangle. Okay. Now the second triangle, she went 1.20 kilometers, and I believe it was 28 degrees. Let me double check that. Yeah, 28 degrees east of south. Okay. So we want to find this triangle right here. Again, this side is going to be 120 cosine 28. This is going to be 120 sine of 28. I'm sorry about the handwriting. As I explained in the other video, which didn't load up, the nib, the tip of my pen, stopped working. So I'm just drawing with my fingers, which is not ideal. Again, grab your handy dandy calculator. Run these numbers through. And we get about 120. It's really 1.2. Let me correct that. Is that right? Yeah, 1.2 kilometers. Okay. So this is 1.06 kilometers. And this is 0.563 kilometers. Now notice that one of them is in meters and one of them is kilometers. I'm going to change everything to meters, or kilometers rather. So that's why I have 0.563. So this is how far south he went on the second time. This is how far east he went on the second time. Okay, so that's step one, right? We've now taken both triangles, we've broken down into its component parts. Step two is we combine them, okay? So we know that during the first leg, 461, okay. Well, 461 meters or 0.461 kilometers south. The second leg, you want 1.06 kilometers south. So because we move south both times, we can add those together. You get 1.521 kilometers south. Now notice on the other one, on day two, or on part two, rather, not day two, because it was all on the same day, Emerald went 0.563 kilometers to the east. Now notice over here, on the first trip, part of her trip, she went 132 meters to the west. East and west are in opposite directions. So what we're going to do is we are going to subtract 0.132 kilometers west, and we're going to get 0.431 kilometers to the east. Okay? Because we went south both times, we add those together. Because we went east one time and west the second time, we're going to subtract those. Okay? So now, that's step 2, right? We add and subtract the component parts. Step 3 is we use that to build a triangle. So we know we want 1.5 kilometers to the south, 0.431 kilometers to the east. And what we're looking for now is this vector. So we need to know how long it is and what its angle is. Now you should have in your notes that how we figure out the magnitude, which is how long it is with the Pythagorean theorem. Okay, so we're going to go the square root of 1.5 squared plus 0.431 squared. And that is going to give us the magnitude of, give me just a second while I pull up my calculator. And that gives us 1.6 kilometers. Okay, now we need the directional piece. And again, in your notes, you should have that what we use for the directional piece here is inverse tangent. Inverse tangent of opposite over adjacent is going to be our angle. So here the opposite of our angle is 0.431. The adjacent is 1.5. Drop that into the calculator. We get 16 degrees. So our final answer here is the coffee rapid response team needs to travel 1.6 kilometers at 16 degrees. And that is going to be east of south. I thought it stopped right there at the very end of the video. I was about to scream. Not that you would have heard because the video wouldn't have recorded. So why east of south? Because we're heading east. Then we rotate to we're heading south. And we rotate to the east. And that's where our angle is being measured. It's right there. It's from the south, swinging east. If we had measured the angle this way and had been looking at like a triangle like that, or at least, yeah. So if we had been looking at this angle right here, that would be south of east. Okay, hopefully that makes sense with how much we've done that. So this is a guidance. Hopefully this gives you a lot of really good ideas on what to put down on your cheat sheets, especially now since you know basically the setup of all 3 problems. Oh, the vector problem on the final. Continuation of the Emerald story. Same exact idea, just slightly different numbers. If you have any questions, please let me know. Other than that, keep studying. It is 1 a.m., so I'm going to try and get this posted tonight so that first and third period have at least 24 hours to deal with it before their final. But again, this probably means I will not be getting to grading and posting all of the vector tests today, but definitely tomorrow. Have a wonderful evening, everybody. I will see you all not tomorrow, just later today.